In this video, we're talking binomial distribution. Now look, these distributions are like functions or boxes that we fit experiments or situations into. And so when we read an experiment or a situation going on, we try to fit it into various distributions so that we can then evaluate probability, maybe find mean, standard deviation, and define other characteristics of that experiment. And so think about these distributions as functions that we're trying to learn so that then we can tackle bigger situations. This distribution builds off of a previous distribution, that probability distribution we talked about before. Those distributions were recognizable because of those tables where we had probability we could simply pick from, and we could talk about probability, yes. We could talk about mean and standard deviation as well. For the binomial distribution, it's similar that we're going to have these similar tasks to perform, but the way in which we accomplish them is a little different. So let's get into it. And that's really what the introduction here is all about. So if you recall from these probability distributions or table distributions, we can think about that one of flipping a coin, where I think of the number of heads that I get, the number of successes, the random variable, if you will, of x equals 0, 1, 2, 3, and we had various probabilities. Here I have the decimals as opposed to the fractions that we had before. What we're interested in is this binomial distribution. If we can think about these random variables as successes, 0 successes, 1 successes, 2, 3, we can try to separate this into this win or lose mentality, this binomial distribution. Now, this distribution is pretty special. It only really works for discrete probability or discrete random variables, and it has to do with a fixed number of independent trials. That is a very important characteristic. We'll refer to these fixed number of trials as n. We'll get more into that in a minute, where I can look at that, much like my flipping a coin example, where I'm only interested in what we define success to be, and then everything else is failure. And that success are the two ingredients that we need, that we're repeating something a couple times and that they're independent. And additionally, that we have this notion of success, two ingredients to build up this distribution. Of course, as you can see below, we are going to be using Excel in this binomial distribution, mostly to compute probability. Much of the mean and standard deviation we can do by hand. Let's dive into this distribution. Let me slide over here. So the first thing that we talked about, what are the ingredients for binomial distribution? The first one is a trial. All right, a trial is you repeating something over and over, and each individual attempt is referred to as a trial. And so we're going to have to end the number of trials in total. How often are we repeating? For our little flipping of a coin example, well, we flip the coin 3 times. And so there are 3 trials that we have. And the big point that we need to always make sure with binomial distribution is that each of these trials are independent of each other. Of course, if I'm flipping a coin, yes, every time I flip it and I go to flip the next time, they're independent of each other. There's no influence from one to the next. Independence is an important check to make sure we have. Now, within each of these trials, we're going to refer to an outcome that we're interested in, and we'll label that success. That can be something like landing on heads, or maybe if we're rolling a dice, maybe we talk about 1 or a 2 as success. Sure. And then anything else is failure. Now, we'll use symbols to represent these probabilities that each occurs on each individual trial. And so P is going to be our probability of success. We need 2 ingredients to make the binomial distribution work, and it's n number of trials, and it's P, my probability of success. On the flip side of that, if you have P, your probability of success, you're going to have Q, your probability of failure. We don't rely too heavily on Q. There are some components or some calculations you can do with Q, but we don't necessarily dive too much into Q, the probability of failure. One of the friendly things is that these are complements of each other, the success and failure. And so the formula, if you want to find the probability of failure, Q, is just 1 minus P. Once I have those 2 ingredients, N, my number of trials, and P, my probability of success, well, then there we have it. We're going to get a binomial distribution. Again, binomial because there are 2 outcomes, success or failure. A nice example, if you refer back to the flipping of the coin example, 3 times, that gives me my number of trials. I'm flipping that coin 3 times. There's 3 experiments taking place. And if I call my random variable or my success to be the number of heads, well, then P, my probability of success, is of course 2 sides to a coin, 1 divided by 2, or 50% is my probability of success. And once you have those 2 ingredients, N, my number of trials, and P, my probability of success, well, then we can actually use this framework, this function, binomial distribution, to then build out things like probability, the mean, and standard deviation. So let's see those definitions for how to compute probability, yes, and also the mean and standard deviation. So if you remember from tables to do probability, it was simple. For tables, we just picked our probability. For a binomial distribution, it's a little bit more involved. Here we have it. This is our probability. For binomial distribution, we're going to need a tool in order to calculate probability. The tool that we'll use is Excel, and Excel has a nice function. You'll remember sum or average or median. Our function here is going to be, this is a friendly one, binom.distribution. And this is the function we'll use to compute probability. This function can do two different kinds of probability, and they look like this. Let's say probability x is equal to k, maybe some number like 3. Or maybe if we're talking about a number of successes, we could say something like 1. I'm interested in getting 1 success. Well, then I would type binom.distribution, k, that would be 1. How many successes do you want? And my number of trials. If we're doing our little coin example, that was 3. I would say P, my probability of success, was 0.5. And then this 0 or 1 really just tell you whether or not you're doing cumulative or not. If I want to do less than or equal to 1, then I'll put a 1 at that last input. This 1 also is the same thing as literally typing the word true, or 0 is the same thing as typing the word false. 0 and 1 is just a bit shorthand for us. And so if I type 1, 3, 0.5, and 0, this will calculate the probability of getting 1 success for my flipping of a coin. Now you can look at the table to confirm this, or you can literally type it in Excel and you'll find that the answer is going to be 0.375, or 3 divided by 8, just like you can read from the table. And so a lot of what binomial distribution is pretend we have those tables for table distributions or probability distributions. And you can imagine listing them out, maybe 6 different columns, and that table's pretty big. Binomial distribution, though, can handle much larger experiments. Say maybe you're repeating a task 1,000 times, right? You don't want to have to read probability from a table that's somehow 1,000 lists long. And so this binomial distribution can handle these much bigger events. 2 ways to do probability. If you have equals to, we refer to that as a PDF. Stands for probability density function. And less than or equal to, that stands for cumulative density function. And we have those inputs. We'll do some examples here in a minute. In fact, I typed some up for you here. And this is what they look like on our formula sheet. Binom.distribution, you got your inputs here. Again, 0 is the same thing as writing false. And then if you have cumulative or less than, you got to get out of the way here. Same 3 inputs, K, N, and P, but then your last input should be true or a 1. And then I'll know, hey, look, you're doing cumulative. You're going to get everything less than this value. So that's probability. Again, a bit more difficult, especially if we compare it to those table distributions. If you remember the mean and standard deviation, they were quite difficult for those probability distribution functions. We had to multiply and add big quantities together. Binomial distribution, much more friendly for the mean and standard deviation. Again, these 2 big tasks that you'll be asked to perform. For the expected value, often referred to as the mean or the expected value of x is always a random variable, is just n times p. You remember we needed 2 ingredients? Those 2 ingredients are fundamental. They'll give you the mean if you multiply them together. For the variance, or sigma squared, it's n times p times 1 minus p. There's an alternative form to write this formula, and the formula is just n times p times, this is q. And so if you see the alternative form, it's the exact same formula. This one's, I think, a bit cleaner. So we'll need the mean one and also the standard deviation, which is right here. 1 little sigma is equal to the square root of n times p times 1 minus p. So these 2 formulas are given to you right here. Mean formula and standard deviation formula. So make sure we know, hey, look, if I have binomial distribution, again, I have those 2 ingredients, n and p, friendly thing. The formula sheet tells you what those 2 ingredients are. Then I know to compute probability, as we've seen up top, and the mean and standard deviation. Let's dive into the nitty-gritty and see some examples in practice here. Consider the experiment of tossing a fair coin 16 times and counting the number of times the coin lands up heads. So that's our idea of success. The first question is just introducing, hey, what distribution does it follow? At this point, I'd encourage you to think of, okay, look, for right now, there's only two distributions that we have at the moment, and it's the probability distribution, or as we more fondly like to call them, table distributions. Those ones are pretty quick to identify because we literally can observe a table. The next distribution that we have in our back pocket is binomial distribution, but we should be looking for these two ingredients, and that is n, comma, p. This first one kind of leads us along that way. It says, hey, look, what distribution does this experiment follow? If you don't know, we have these two distributions so far. You can pick them out of a hat. Else, maybe our little hint helps. It says, what is the number of trials, n, and what is our probability of success? So again, I'll write here, n equal to our number of trials is how often we're repeating something. Well, for our experiment, I'm flipping a coin. It's landing. Okay, I pick the coin again. I flip, it lands. And I do this again. In fact, I'm doing that 16 different times. And a little question that we should be asking ourselves is this independence. And in this case, yes, they're independent. Every time I flip that coin, it is afresh every time. So first ingredient, done and dusted. The next one is P, my probability of success. And here, when we're flipping a coin, we're interested, what are we defining success to be? In this case, it says, hey, look, I'm interested in a coin landing up heads. And so our notion of success is landing up heads. Well, on a coin, that's 1 divided by 2, or as a decimal, that's simply 0.5. Since I have these two ingredients, the question is, what distribution does this follow? Binomial distribution is our response. Now that we have the distribution in place, well, now we can start to answer questions like probability, mean, and standard deviation. That's what this first example shows. Now look, I'll open up Excel in future examples, but for this one, we'll just write out exactly like we would type. And that's what these blanks show. The first one says, what is the probability of getting exactly 8 heads? If we were to write that out, again, I read probability, we're thinking, okay, look, I'll write this part out. If you're following along on the notes, hopefully this is a friendly thing already written out for you. It says the probability that I have exactly 8. To be fancy, I can write x is equal to 8. If you look at the formula sheet, the formulas that are just before it, I know, okay, fits exactly with that first method to compute probability. I should write it like this. Equals, I have binom.distribution. Again, writing it just like we would type it. And then I have 4 inputs to choose. The first input is K. How many successes do we want to experience? For this one, I want exactly 8. So I'll write 8 for the first. The next 2 inputs are my ingredients for the binomial distribution, N and P. Fortunately, we talked about those up top. I should write 16 and 0.5 for N and P. The last ingredient is either 0 or 1. Again, you can get this from the formula sheet that if you ever have equals to, then you want to write 0 here. And then just like that, you'll get a probability here that the probability that x is equal to 8, that I get exactly 8 successes. We don't have to draw a table. I don't need to do a bunch of multiplications. We get it almost immediately. It's 0.9196. And if I round to 4 decimals, it'll be 4. And there's my probability of getting 8 successes, roughly 19 or 20%. Very friendly, powerful distribution, especially when you contrast it with the method we were using for probability in the past. What is the probability of getting 7 or fewer heads? Well, again, I can't write equals. Instead of writing fewer, let me write 7 or fewer. That's like getting, I'll write less than 7. Technically, it should be fewer than because it's countable, but anyways, less than. Or I can write fewer than, less than. We have a symbol for that, don't we? All right, x is less than 7. Although here it says 7 or less, so I should write here equals to is also good. Fortunately for us, I can jump right into Excel now because this fits exactly with what we have on our little formula sheet. I have probability x is less than or equal to 7. This fits that second method for probability. I'll write it here. Just like you type it. Equals, I'm going to write binom.distribution. And just like the example above, I have 4 inputs to put in. The first input is the number of successes that I want, the highest. In this case, that's 7. The very top, K, what value are we comparing it to? Then I have the same 2 middle ingredients, my N number of trials, and P, my probability of success, 16.5. This one's different though, and it's 0 or 1 based on whether or not I have 1 exactly input or cumulative. For this one, I have cumulative, and so I'll write a 1 here, or you would type, if you're using Excel, you type a 1. If you want to get really fancy with it though, you can also write true here. You can also type that in Excel and it'll understand what you mean. And you should get a probability. Let me make sure I'm out of the way here. Probability that x is less than or equal to 7 is equal to 0.4018, roughly 40% chance that I will get 7 or fewer heads or successes. Again, much powerful than looking at this large table and adding up a bunch of different values. This distribution, this binomial distribution, is actually something you can graph, and that's exactly what this chart shows here in the corner. And you can think about this much like you would a histogram or a bar graph. In this case, this is technically a histogram because the order is fixed. I can't somehow move around my 3 and 7. The order is natural here. It looks like when I'm looking at my order here, well, there's a couple things I can observe. Again, on the left, I have my probabilities associated. In fact, we did one of these. The probability that I get 8 successes, exactly 8. We computed it up top, and it's looking like 20% from our table. And then we can see everything kind of nicely is symmetrically cascading out on either side. That's getting fewer successes or more successes on the right-hand side. And so a question we can ask from the graph, much like we talked about mean and standard deviation, well, the mean, also referred to the expected value. How many heads can you expect, that's just the mean, to see after flipping the coin 16 times? This is like asking you, where is the center? Sometimes this is clear. This graph is beautiful. In fact, it's symmetric is the word that we would use. And it looks like the mean is right here in the middle. That is the center. That the mean equal to the center, or where most of your data is located, is going to be 8 in this case. In fact, there's actually a very friendly way we could confirm it, and you could actually just compute it using the formula that the mean is n times p, or 16 times 0.5, and yeah, we get 8 there. And so if we see this nice graph, it's symmetric. I can actually tell you why it's symmetric, and it has to do with that p-value, p equal to 0.5. And since that probability is exactly in the middle of 0.5, go figure, we get a symmetric graph. You'll see in future examples, if I have a different probability, 0.15, 15% chance of success, well, that's going to put most of my data down on the lower end. And so we won't have necessarily this nice symmetric data, which is more common with binomial distribution, to have this skewed one way or the other. This just happens to be a nice distribution, and I can tell you why that is. It's the p-value. A quality control expert at a large facility estimates that 10% of all batteries produced are defective. Bummer. If he takes a random sample of 15 batteries, what's the probability that exactly 0 are defective? And so it's important when we're reading these experiments, we think of these different distributions we have, these probability distribution, table distributions, or binomial. Well, we can look at this. We have 15 batteries that we're checking, and it's like every battery, I look at that battery and I say, look, are you defective? And then I throw it to the side and I pick up the next one. Are you defective? Throw it to the side, look at the next one. So I'm repeating this task, this trial, if you will. I'm repeating it 15 times. And yes, every time I look at that battery, it's independent of the one that happened before it. And then we're saying, okay, look, what's our probability of success as I look at these? This one's kind of strange because I'm defining success, or what we're interested in finding, as a battery being defective. That's what we're going to define as success. And so the probability of me getting this success is 10%. I'll write it as a decimal of 0.1. Again, once you can identify these two ingredients, we got binomial distribution, and now we understand how to do probability, and also we'll see the mean and standard deviation as well. For this example, as we do solutions, I'll pull up some Excel and we can see this in practice as well. The first one, what is the probability that 0 are defective? Before I whip out Excel, let's first write out the probability that we're interested in. Probability that x is equal to, because I want exactly 0 defective batteries. Once I have it in this form, well, hey, now we're good. We can look at our little formula cheat sheet and understand how to compute probability. So let me bring up Excel and we can have an accurate display here. So again, 0 successes, I can write this as equals, so I'm typing it here, binomial, so binom. And again, one friendly thing is as you start to type, we can see it here, binom.distribution. I can double click this or I can hit tab, whatever you prefer. And it's going to ask me, look, what inputs would you want? Again, 4 inputs, they're on the formula sheet. You don't have to memorize these. They're also on Excel as well. I want n, my number of successes. I'm interested in 0 of those. I don't want any successes. That's what k is. And then it should of how many trials, how often am I repeating this experiment? That's n. We identified that above as 15. P, my probability of success, is 0.1, or you can write 1 divided by 10, or you can even write 10% if you'd like. Excel understands what you mean. And the last input is, look, is this cumulative or not? You can type in just like the formula sheet says. For this, we're not interested. You can write 0 because we have equals to, or you can literally type the word false here. And it'll say, oh, look, I know what you want. You want a PDF 1 function. I'll do 0 to stay consistent. Once we type those inputs, boom, we get our probability, no problem. 0.205891, just like we have on our PowerPoint slides there. And so again, this is the work that we would type in here. In fact, let me type it in mostly for posterity's sake. So there's our probability computed for us. Let's look at the next one here. What is the probability that at most 2 are defective? We need to write this as a probability. Up top, this will be the probability that, and we can write in parentheses what we're interested in. The 2 is the most I can get. So I would write this in inequality. I can write x is less than or equal to 2. Again, the second we have either of these formed equal to or less than equal to, I can jump right into Excel and I can write out exactly what we're going to compute. So let me jump down here. In fact, I'll write it here. Probability that x is less than or equal to 2. And here we go. I'll write binomial.distribution. And then what are my number of successes? Again, this should be the number that we're comparing to, always less than 2. Number of trials, 15. Probability of success, 0.1. And cumulative true, or I'll just type in a 1 there. And we should have all of these inputs typed in similarly. So again, only difference here, make sure you notice the 1 or true at the end versus 0 or false at the end. And we should get a probability just like we see up top. In fact, let me write it real quick so we have it for posterity's sake. Roughly 81 or 82%. Let me build out this a little bit because we're going to look at a complication that often emerges with binomial distribution that so far we've avoided. Let's dive into what that complication is. What is the probability that more than 6 are defective? Here's why this gets complicated. If I want to write more than 6, I can write that. In fact, I'll write it right here. Probability that x is more than or greater than 6. If you look at your formula sheet or even Excel, there's only 2 ways that we can give you probability, and that's equal to one specific value or less than or equal to. There's nothing in between. And so I need to convert this x is greater than 6 into less than or equal to. Let me show you how. And we're going to use this little table here. In this table, I have all the different outcomes I could possibly imagine for success. In fact, let me circle what we want. I want more than 6. And so I don't want 6. I want 7 successes, 8 successes, 9, 10, 11, 12, 13, 14, 15. This is what I want to calculate. Unfortunately, there's no way that I can calculate greater than. In order to do that, I'm going to do a little workaround. And we've actually done this in the past with complements. And this is what it looks like here in binomial distribution. Let me take 1. Again, 1 is everything in the whole wide world. And say, look, something's going to happen. And then I want to remove what I don't want. Remove or take out. I want to take out the probability that I am down over here because again, 1 is too much. It's everything. So let me remove or take out what I don't want. That's 6 I don't want, 5 I don't want, 4, 3, 2, 1, 0 successes. We can actually write this in inequality. I can write this as x is less than or equal to 6. And now I've captured 1 everything for probability minus what I don't want. X is less than or equal to 6. And now we can actually compute our probability. Again, we couldn't do it with greater than because there's no function for calculating greater than for probability, at least not in the tool that we're using. And so then I have to convert it. We can do so pretty friendly here. Let me type out exactly what that looks like here. So there's a couple different ways to do this. Let me do it directly. Again, my probability should be 1 minus probability that x is less than or equal to 6. If I'm going to type that in, I can do so. I'll write equals 1 minus binom. I'll just type in bin. I can scroll down a little bit. There it is. Binomial distribution. I can hit a tab or you can double click. Type in binomial distribution. Number of successes. That refers to only this probability we're computing. 6. Number of trials is 15. Success 0.1. And lastly, this is cumulative. We have less than or equal to. I'll write a 1 for my last input. And so I'll have it here for reference here. That when I need to compute my probability, I can do so. I just have to remember I need to do 1 minus because we have greater than. And that's our only additional complication there. And hopefully the table that we showed here highlights exactly how to perform that calculation. If you have greater than, no problem, just do 1 minus and figure out what that probability should be. Let me write that probability here, and then we'll continue on to the next example. Whew, barely fit it in there. Let me open up back to PowerPoint so that we can continue on with the next example. So now that we've done probability, maybe I want to ask the question, look, I'm producing these batteries. How many batteries can you expect to be defective? Again, whenever you see expected, it should be sending alarm bells off or association alarm bells, because that expect number is just the mean. I'd encourage you to write the formula. It's the best way to keep it in mind. Because we have binomial distribution, I don't have to go through all these different formulas. We know the formula. Because we're binomial, I know this is going to be n times p. N, my number of trials, times p, my probability of success. 15 times p1. And I can multiply these. I should get a number like 1.5. And if there's no rounding that's specified here, I can simply box this in, and then I can denote that this 1.5 refers to the number of defective batteries. 1.5, about 1.5 batteries are going to be defective. That's what I can expect out of this sample of 15. Next up, what is the standard deviation of the number of defective batteries? Standard deviation, again, once we understand what function or umbrella we're in this case, standard deviation, I have binomial distribution. I know that's going to be the square root of n times p times 1 minus p. And again, I encourage you to write that formula. That if we do make silly mistakes, at least we have some good supporting evidence. Additionally, we go back and look at it. We have that for our learning resource. I'll write out what you would type in Excel. Excel can compute this for you. I would type the square root of 15 times p. It's going to be parenthesis 0.1. And then times, I could write another parenthesis, 1 minus 0.1. If I want to write that in Excel, all right, if you already have it open, it's very friendly to calculate. If I need to do the square root, we can do so. Whenever you do calculation, make sure you type in equals. Square root is just squirt. And then I can type in 15. If you want to do multiplication, you can do a little star, or you can do parentheses, 0.1, little star, little parentheses, 1 minus 0.1. And then you end that bracket. And it looks like our standard deviation is going to be 1.16. And so we can compute these much more friendly than probability distribution. Nice formulas to compute. What can we do with those things? If the number of defective batteries is more than 2 standard deviations above the mean, the factory will shut down the following day to give time for maintenance. We certainly don't want that. At least the shutting down, the maintenance part is good. What is the probability that the factory will shut down? Oof. Certainly we do not want that, but it's something that we can understand probability. So let me write that out. Again, it says probability. We can figure this out. It says here probability that X, and we're interested in some value. Let's go back up top. It says the number of defective batteries is more than 2 standard deviations above the mean. More than, whenever we hear more than, we should be thinking greater than. So I know for my little probability notation here, I should be writing greater than. And now they're talking about 2 standard deviations above the mean. 2 standard deviations, that's just 2 times our standard deviation above, meaning I want to add it to the mean. And so this is the value or the X quantity that we're interested in computing. We can calculate it here pretty friendly. That should be 2 times our standard deviation we have up top is 1.16 plus our mean that we have is 1.5. If I multiply then add them, again I cheated, I did it right above, 3.82. And that's the value. When they say 2 standard deviations above the mean, they want to say 3.82. When I look at my probability though, we're in a pickle, because when I look at my formula on how to compute probability, everything is always less than or equal to. So I need to convert. I don't have that. I have greater than. So how do we compute probability? Whenever you have greater than, no fears. I can always write this as 1 minus the probability that X is less than or equal to some quantity. If you're having trouble understanding what value you should put here, let's refer to the table above to help us pick. So I want more than 3.82. Well, then 4 would certainly be in that category, more than 3.82, 5, 6, 7, 8. All these different values are what we quote unquote want to compute. And so if I take 1, again, 1 is everything on this list, everything that we could possibly compute. But then I want to remove or take out what I don't have circled here. In this case, that's 3, 2, 1, and 0. So X is less than or equal to 3 will be that removal here. And now once I have it in this less than or equal to, now we can jump right into the calculation. Let me slide over here and get out of the way. I'll write in here equals 1 minus, for my probability, it's binomial distribution or binom.dis. And again, I'm writing it just like you would type it if you had Excel open. And we're looking for 4 inputs. The first one is my number of successes. In this case, we figured that value was 3. Then I want n my number of trials, 15, p my probability of success, 0.1, and lastly 0 or 1, depending on if we have single, that's an equal value, or we have less than or equal to. Well, that's what we have here. So I'll write a 1 here. And we'll get, it looks like a probability as x is greater than 2 standard deviations above the mean is equal to 0.05. We'll leave it at 2 decimals and we'll just leave it there as 5%. But here's what we can do now that we understand this is the probability that the factory shuts down, which is certainly, maybe for an investor, is not what we're interested in, but we can actually quantify the likelihood that this happens. Let me slide over here. It's a little better. So in discussing this distribution, there's some shorthand that we can write for binomial distribution with these 2 ingredients. And it looks like this. The shorthand says that, look, a random variable, x, follows a certain distribution. So far, this is the only distribution right now that we have this format. B for binomial distribution, and there are 2 ingredients, n and p. Let me demonstrate this notation in the next example. Suppose Bram is taking a multiple choice 11 question quiz where there are 5 choices for each question. Suppose he randomly guesses on all questions. It's not looking too good. So the big question is, what distribution does this experiment follow? And my little hint there, what is n, what is p? And so in thinking about this, I'm looking at this number of trials. I'm repeating something over and over. How often am I doing it? Well, for this 11 question, we're looking at this quiz. In first question, we're like, I don't know, B. Next question, we're like, I don't know, C. And we're just randomly guessing on each of these. And so for each question, those are our trials. How often are we doing this experiment? It looks like 11 different questions. Now for P, this is my probability of success. For this example, we're guessing all the questions and we'd like to get correct. Well, there is 1 correct answer. So we'll do this the old-fashioned way for probability. There's 1 correct answer out of the 5 questions in total, or the likelihood that I will get each question correct is 1 divided by 5 as a decimal. That'll be 0.2 or 20%. Once we have these 2 ingredients, we're golden. I know this is going to follow the binomial distribution. Or if I want to use my new shorthand, I can say, look, x, the random variable, follows binomial distribution where n is 11 and p is 0.2. And so this is a shorthand way to condense this exact phrasing, binomial distribution, n and p. What can we do with that information? A 60% is considered a passing score. How many questions must Bram answer correctly to pass? Well, I know that there are 60% of 100% or of the entire test is passing. So I need 60% of the 11 questions is how we would write this. I need to get this many questions correct. So this is going to then make us think about 60%. I can write that as 0.6 of, meaning multiply, times 11. And this will give me the number of questions I need to answer correct. If you multiply 0.6 times 11, you'll get 6.6 is how many questions we need to get correct. Although I don't think Bram can somehow get 0.6 of a question correct. At least there's no partial credit denoted here. And so let me round this thing up to 7. That in order to pass this quiz, I need to get 7 questions correct. Let's see what we can do with that. Let me slide out of the way. What is the probability Bram passes the quiz, provided he guesses on every question? Passes the quiz. Remember, that's going to represent a 60% or 7 questions correct. If we look, this little chart should help us out. Let me first write out what that looks like. If I want to pass that quiz, then I need to get 7 or more correct. And so I'm looking at, for the probability that this occurs, the probability that x is greater than or equal to 7. Again, if I get 7 correct, boo for us, we passed. The problem is, for binomial distribution, I can't do greater than or equals to. I can only do less than or equal to. And so I need to convert. No problem. If you ever have greater than, let me write this as 1 minus the probability that x is less than or equals to. And I need to figure out what I need to remove, let me slide on the other side here so we can view our number line. So this is the number that I want correct. 0 questions correct, that'd be a complete fail. 1, 2, 3, 4, all these numbers are fail. I want greater than or equal to 7. So this is what I want. So then what do I want to remove? It's everything below. This is what I'd like to remove. 1 minus probability x is less than or equal to 6. There are some formulas out there for how this will always work. If it's equal to, then you subtract 1. If it's not equal to, then we would write 7 here, for instance. So here, once I have it in less than or equals to, I can write it just like you would type it in if you have Excel pulled up. This would be equals to 1 minus, I should write binomial.distribution. In parentheses, we want k, number of successes we're interested. In this case, it's 6. I want n, my number of trials. These are 11 questions. What a trial that would be. P, my probability of success, 0.2. It's a 20% chance I'll get a question correct. And then, of course, a 1 here. The last input is always a 0 or 1. 0 if we're looking at equals to. 1 if we're looking at less than or equals to. Once I type that in, like magic, we'll get a probability, no problem. And that probability will be equal to 0.00197. Or if you had to round that to 4 decimals, you would write 0.0020. To conceptualize that, that's 0.2%, not even a full percentage point. Bram, the outcomes are not looking in your favor, but we can actually quantify the likelihood that if we guess what it'll be like. That's why oftentimes we have a lot of confidence in building them, because if you walked into that blind and randomly guesses, chances are you're not going to pass, which is why they're often used. What is the probability Bram correctly answered between 5 and 7 questions inclusive? It means I want to include those endpoints. So let me write this between, again, x sitting there in between 5 and 7. If I wanted to write this out, I'd write this as the probability that 5 is less than or equal to x is less than or equal to 7. That x is literally in between those 2 endpoints. And one of the big qualms with binomial distribution is we have to have less than or equal to, which I certainly don't have. If we look at this right half, I actually do have less than or equal to, don't I? X is less than or equal to 7. So let me just write that part, and then we'll get into what our complication is in a moment. This will write as probability that x is less than or equal to 7. Problem though, if I look at what I want over on my little table, I circle it. I want 5, I want 6, I want 7. This right here is all that I want. But if I look at what I computed here, probably x is less than or equal to 7. That's 7, yes, 6, yes, 5, and this keeps going and going and going. This represents the probability that x is less than or equal to 7. It's way too much, and so I need to take out or remove what I don't want. That would be minus the probability that x is less than or equal to some quantity. This should give you a little bit deja vu, and the reason why is because actually the way that we could read this left half is this is x is greater than or equal to 5. Well, remember, we can't do greater than equal to. We have to do 1 minus. And that's what this x is less than or equal to 7 accomplishes. It is the 1 part. It's the too much probability, and we're removing what we don't want. We can see from the table here, what do I want to remove? I want to remove the 4, the 3, the 2, the 1, and the 0. And so I'll write here 4. So if I want to calculate that x is between 5 and 7 inclusive, I can do so by looking at the right-hand side, probably that x is less than or equal to 7. Oops, too much probability. So I'm going to minus, take out the probability that x is less than or equal to 4. When we're computing probability in this way, you can actually type in binomial distribution for the 7, binomial distribution for the 4, and subtract them in one cell. But mostly for convenience sake, let me write them both out in separate cells, and we can subtract them after the fact. So if I look at this first one for 7, I can write this as binomial.distribution, and I need my 4 inputs. The first one's k, 7. In this case, how many successes we want. There are 11 trials. It is a 0.2% probability that will succeed. And lastly, a 1. And I can see my probability here computed for us. For the second one, if I want less than or equal to 4, as we've done, I'll write here equals binomial.distribution. In this case, 4, 11. If you want to write 0.2, that's fine. You can also write something like 1 divided by 5 here as well. It'll give you the same result and also a 1. Again, that's P, my probability of success. It'll take fractions, it'll take decimals, it'll take percents. So just to highlight that here. If I want to compute my probability, I can. Let me write it over here, give myself plenty of room. This is going to be for the x is less than or equal to 6. If I look over to the right, that's 0.99976, very close to 1. For my next probability, it's minus 0.94959. Close to 1, but not quite as close. If we subtract those correctly, we should get an answer, a final probability of 0.0501. If I'm going to round that to 2 decimals, we can do so. That's going to be 0.0502. Keep in mind, for conceptual purposes, that's roughly 5% chance that we'll get between 5 and 7 answers correct, including the 5 and the 7. And so when you have greater than, think 1 minus, we can handle that one. If you have between, it does require more work, but it's similar to the 1 minus that I look at the right-hand side, x is less than or equal to 7. Buoy for us, we can calculate that one outright. But then I need to subtract 5 is less than or equal to x, or better yet, as we read it, x is greater than or equal to 5, which is where we get our minus. So between, we can handle in this way. Here's how we can look at our distribution. Let me slide over here. So this is a distribution of exactly this experiment. I talked earlier about, depending on that p-value, it's going to skew our graph one way or the other. In this case, I have a smaller p-value, 0.2, and so it's going to move most of my data over to those smaller values. Look at the probability that we'll get 9 successes here. That's most of the questions correct. Again, there are 11 questions in total. 9 correct. I'm thinking it's not likely. In fact, the probability isn't even showing up on my vertical scale. So this is the distribution. We could see it's certainly skewed in a certain direction. And so looking at this distribution, discuss the skewness of the graph. What does the graph say about Bram's chance of passing the quiz? We could discuss things like the mean, for instance. We could estimate it from the graph that maybe it's roughly, maybe a little bit larger than 2. Again, we'd like to think that it is 2, our biggest response, but that would be the mode. But because I have this longer distribution, this tail pulling the mean in this direction, that mean is going to slightly be to the right of where most of the data is located. So maybe something like 2.5. I know the exact mean, but we'll leave it at 2.5 as a rough guess. And so what does this skewness tell you about his chances of passing? Well, I can tell you the average, the most likely outcome, not looking too good, right? 2.5, that's out of 11 to pass. If we want to discuss skewness, again, skewness is always in the direction of the tail. In this case, the tail is on the right side, and so that's the direction of the skew. If you'd like to, for these distributions, you can draw frequency distribution graph, and then you can see, look at that tail pulling that mean toward the right. It's skewed in the right direction. And so this can tell you a couple of things. Again, over here, this is what we considered passing. And because it's skewed in that direction, meaning it's not likely. In fact, whenever we talked about skewness, we talked about that's the direction of outliers or atypical values. And so the skewness tells you unlikely to earn 7+. And that's exactly what the probability told us beforehand. So the skewness can tell us many things. Either we can look at the probability and compute it directly. Look, what's the likelihood that I'll pass this quiz? Or once we understand the distribution in the graph, we can make these inferences without computing probability and simply looking at the skewness or the shape of our distribution. And so here we can wrap with this. Look, this was our big distribution, binomial distribution. And really there's these 2 big tasks that I want you to focus on. The first one is identifying the distribution. Look, I have these 2 ingredients, N and P. Once you identify those ingredients, now we're in this world, we're in this function that says, these are the rules or the way that you play. And so the second thing to pay attention to is what those tasks are. That computing probability, as we've shown many examples, and computing the standard deviation and the mean. So be able to identify this distribution, those 2 characteristics, and understand the tasks that are being asked within it. Probability, single or cumulative, and also the mean and standard deviation. If we can lock that down, well then, hey, look, if I give you a 3rd, a 4th, a 5th, a 6th distribution, well, we can understand identification and then tasks that we can perform within that distribution. Look, if you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.